So my name is Emanuele Pascale. I work within Itachi STS since 2009. My main focus has been safety, reliability testing, B&B. I have spent almost 8 years in France. Basically, I'm an electronic engineer. I have performed further studies, and this presentation is the wrap-up of some of the publications that have been done in collaboration with some French organization. In this presentation, we're going to discuss how reliability can leverage on big data. And we know that nowadays each industrial domain seems to be affected by a revolutionary innovation that aims at increasing the quality of the life. And we are searching for autonomous trains that are running 24 hours, 7 days. We are searching for autonomous plane, self-driving cars. What's the key aspect, the common aspect that brings together all these innovation is reliability. One of the slides that is missing was related to an exercise that I wanted to do with you. When thinking about reliability, often when you want a more reliable product, you have to add cost, because a more reliable product is composed by better components, with more redundancies, with better process. So we are used to associate reliability with cost. But what would be the cost of unreliability? And so in this missing slide, there was the picture of an exploded phone, and my question was, what's the name of the company? I would have asked you, what's the name of the company whose mobile phone exploded on a plane? Nice one, Samsung. So you have to understand that unreliability cost may be very heavy. For example, in terms of marketing, because after 3 years of this event, you still remember the name of the company that was faulty on this aspect. If you take the progress of the stock on the market, you see that the day in which Samsung stopped the production of this phone, stocks fell of 8% in 1 day. So there is really a cost related to unreliability. The context in railway is the following one. There is an historical misunderstanding related to reliability reliability performances of a system. If you take a data sheet of a component and you search for the section reliability, you will find out often one parameter, MTBF or MTTF, like is a mythological parameter that aims at describing the reliability of a system. Even from a standard point of view, from a customer point of view, there is a request in terms of performance described by MTBF or MTBSF, where S means services. So we don't want that our train gets stuck on a line, but we translate it in a figure. Even if Senelec standard required for reliability demonstration is not something that all the parameters are left to the constructor that have to perform this demonstration. And there is no clear way, but it's something that is mandatory with respect to what required Senelec. And finally, there is a scientific community that is divided on one of the main property of the failure rate that is related to the MTBF. Can the failure rate be constant? When we say failure rate constant, means that if you take your system at T0, the way failure occurred during the time is the same if you make the picture at T0 or if you make a picture after 10 years. From a technical point of view, I have depicted two kind of way of describing this problem. One of them is the exponential distribution, so is the fact that I was talking about. We say that the failure rate is constant over the time, and you can use a more complex system in which the failure rate is depending on more parameters. In this case, I have put on the slide variable distribution. But it's not the only one. There are plenty of reliability distribution. What's interesting is that in one case it is constant, in another one you have put your attention on the beta factor because we will discuss after. In the known limits of constant failure rate paradigm, you can have a look to these known limits when you look at reliability over the time. Classic reliability of a system as the path of a bathtub curve. That is, you have a reliability that increases at the beginning of your system because you have to tune your system, because you have quality side effect. Then you have a period in which the failure rate is constant, and after that your failure rate is increasing because your system is experiencing age, is becoming old. But in reality, the reality is a little bit more complicated than theoretical models. And when you start, when you measure an increase or a decrease of the reliability, so an increase of failure rate, is it because your system is going old, is getting old, or is it because you have intrinsic wear out or latent defect? When speaking about reliability, you know that each system is designed in a way that you know the limit that your system have to comply with, and you take some margin. When you put this margin, is a difference, is the distance between the green bar and the red bar. You have to know that these two bars actually have a distribution. This distribution can vary over the time, and you experience failure when this distribution meets. The reliability data references that are used and are referenced in CENELEC standards have trends that start since 60 years with the first reliability data set, that is the Mill handbook, that was in military context, that was based on constant failure rate bounding. And this, since it has been the first pillar of reliability, all the other reliability data reference that have been come after have imitated this kind of behavior until nowadays, where the recent version of CENELEC standard keeps citing these data references. The fact that there are doubts on the fact that MTBF or failure rate can be constant over time has been somehow demonstrated at the end of 90 years, where Jones and Hayes have took 6 different boards with different kind of technologies. They have tried to apply this reliability data set, and they have measured the deviation from field behavior, and they have discovered that there is a lot of variability. So that the question is, are these data references represented? To understand the limits of this approach, you can take three machines, three equivalent. One of them is experiencing failures over a given time in a randomic way. For another one, the failures are at the end of the observed period, and for another one, they are at the beginning. If you make the calculation according to standard approach, you have that the MTBF is the same, but you understand, looking at this figure, that the physical representativity of the failure is not the same. Another limit is if you take one board that is running for 1 million of hours and it experiences one failure, it has the same MTBF of 1 million of board that are running for 1 hour, and each of these 1 million of board is experiencing a failure. So they have the same MTBF, but you understand that things are speaking differently. Oh, okay. This was the previous exercise. I took this slide at the beginning, so this was the famous mobile phone that exploded, and this is what the -8%. The idea of the approach that I discuss here brings together reliability and big data. It is based on field return data, so in order to build up more complex reliability distribution, you need data, real data, instead of a static model that are associated to a classic approach. And when you try to face this new wave of models, you have to face with some limitation. One of them is problem of censoring. The colleagues were speaking before and they said big data is sharing. Yes, big data is sharing, because if you want to build up your models using only the information that you own as field return, there will be a strong problem of censoring, and data about failures have to be shared by construction, by operator, and by industrial provider. So this is also related to the availability of data, because what is the instant in which failure occurs? Is it the instant in which the system goes off? Is it the system in which the operator will communicate you? Is it the system? Is it the time in which you are measuring it? You don't know. So there is censoring. So to go on, we can say that the classic model can be seen as a particular, a specific model of a more general and more complex distribution that is, for instance, the Weibull one. To build up a reliability model based on Weibull, you need this failure, and you have to plot it over the time on a Weibull chart. And you are able to calculate the famous beta I was discussing before. The beta will tell you if your system is at the beginning of its life, in the center, in the middle of its life, so we are in the context of constant failure rate, or if it is experienced wear out. In this case, it has been stressed to show that you can have cases in which the beta is very high and is greater than 1, so you are experiencing a wear out. And if you want to bring back to MTBF figure, because everyone seems to speak only this figure, you understand that in case of exponential distribution, MTBF is more than 1 million of hours. If you report it to Weibull, you have just $32,000. So there are 2 orders of magnitude between the 2 figures. And even from a graphical point of view, you understand, you can see that on the left, the failure rate in one case is increasing over the time, in another case is constant, so the red versus the blue. The reliability in one case is going to 0 slowly, in another case is dramatically going down to 0 quickly. There is a way to, so once you have been able to collect this data, there is a way to build up complex model, to enhance, to have preventive maintenance tasks tuned. This must be done including the cost of a system. So you know that there is a cost related to preventive or corrective maintenance, is the fact that you are replacing your board. And you have the consequence, the cost of the consequence of your failure. So there is a sort of arbitration between, do I wait for the system failing, or do I anticipate and I replace my system? With some formulas, I don't want to bother you with the formula, but you can easily calculate the average cost of corrective maintenance and preventive maintenance. You can make a ratio, so you can say that if the cost of preventive maintenance is more than the cost of corrective maintenance, I need to replace my system instead of waiting for my system failing. So from a mathematical point of view, you can calculate the minimum of this function and identify what is the best time, best moment to replace your system. Of course, as I told you before, you need to, as I told you before, you need to bring with you the relevance of the cost. Because there might be some cases in which your system is experiencing wear out, but the cost of the failure is not important. There are some cases in which you need to understand, you need to replace your system because the cost of the failure will be very important. This is a case in which customers require penalties for unavailabilities, for example. And I knew recently that on some lines in France, there are also indirect costs that are reported to the provider, meaning that if a train got stuck on a line, all the costs for food, hotel, and so on of the people that are on the train can be bring back to the provider of the signaling system. So you have to take care about that. When you take all the minimum points, so you can fix the cost and provide the beta, you can fix the beta and provide the cost, so you can have this kind of plot. And you can, once you have collected the data about the behavior of your system and you know what is the cost, you can understand what is the optimum time to perform the maintenance. Of course, when you move on the left of this graph, you are increasing task of maintenance, you are consuming more boards, you are wasting more, let's say, useful life, maybe enhancing or increasing the time and the way you perform maintenance tasks, but you are reducing the risk of a failure before the time, and you are reducing indirect costs. So there is a numerical example for the one that are interested. So you have systematic preventive maintenance that is, according to this calculation, has to be performed each 3 years. To conclude, in order to have the maintenance optimization, you have 3 pillars. You have to rely on complex reliability model instead of simple one that are related to historical reasons, as I explained before. So you can adopt weighted distribution or more complex model. You have to adopt more parameters than the simple MTBF. You have to rely on big data, so you have to optimize logbook of after-sales department, and you have to share information with the operator about failure. You have to think about your system in an intelligent way and in a proactive way with respect to reliability, in the sense that your system has to be able to collect relevant data. One of them is the total working time, how many times the system has been operated. And finally, you can, with a look-back feedback, you can improve the design of your system, and you can tune and have a portfolio of system that is deployed and that is tuned on the need of the customer. Thank you for your attention.